Last time we talked about complex eigenvalues and how to handle that. And no surprise, when we have complex eigenvalues, sines and cosines, a lot like we had before. That leaves us with one discussion. What about repeated eigenvalues and what goes on? Well, if we step back to when we had our constant coefficient differential equations, we saw that repeated roots usually meant we had to bump up our solutions. We always had to multiply by powers of t or x or whatever the variable was. Does the same thing happen here? Well, not quite. So it's a little bit more interesting. And so let's take a look at an example. So we have a matrix A, minus 6, minus 7, 7, 2, 3, minus 2, minus 4, minus 4, 5. And we're asked to verify that we have eigenvectors. Well, how does one verify eigenvectors? Well, we start by saying what's the equation for an eigenvector? And we just plug in. So to verify, what we're checking is, does A times our vector v equal lambda times v? So we have v. We haven't been given lambda, but we should be able to figure it out. So we're going to go through and carry out the computations. We're going to take our matrix times our vector and say, does it look like a scaled version of the vector we started with? Well, we have 3 vectors, so we're going to get a lot of practice. So first off, we'll start with our first vector. We copy our matrix down, and of course, being careful, minus 6, minus 7, 7, 2, 3, minus 2, minus 4, minus 4, 5. It doesn't hurt to double check. Oftentimes, one of the hardest things about these problems as we're getting into matrix problems is there's a lot of copying involved. And copying leads to potential errors because it's easy to make a small mistake. So it doesn't hurt to take a second, and make sure we copy things correctly. All right, now we write our vector because we want A times V. So we're going to have 7 minus 2, 4. And we carry out multiplication. Minus 6 times 7, well, that's minus 42. Minus 7 times minus 2 is plus 14. 7 times 4 is a plus 28. Next line. 2 times 7, 14. 3 times negative 2, minus 6. Minus 2 times 4, minus 8. Last line. Minus 4 times 7, minus 28. Minus 4 times minus 2 is a plus 8. And 5 times 4 is a plus 20. Well, let's take a look. 14 plus 28 is 42, which some people think is the answer to life, the universe, everything. But for us, we say, well, hey, there's a plus 42 and a minus 42. Oh, okay, that makes 0. Minus 6 minus 8 is minus 14, and then plus 14, that's also 0. And 20 and 8 makes 20 and 8, 28. And subtract 28 makes 0. Oh, it's all zeros. Now it turns out, true story, that this is the same as 0 times the vector we started with. So we now know that this is an eigenvector, because when we multiplied A times V, it's a multiple of what we started with. And of course, we should make it clear that this right here, this is our lambda. So lambda is 0 for this eigenvector. All right, well, 1 down, 2 to go. But these are nicer numbers, so hopefully it'll work out pretty nicely. So minus 6, minus 7, 7, 2, 3, minus 2, minus 4, minus 4, 5, 1, 0, 1, 1, 0, 1. Okay, so going through. Minus 6, plus 0, plus 7. All right, next one. 2, plus 0, minus 2. Last one, minus 4, plus 0, plus 5. Well, minus 6 plus 0 plus 7 is 1. 2 plus 0 minus 2 is 0. Minus 4 plus 0 plus 5 is 1. Now, does this vector look like a multiple of that vector? Actually, they look like the exact same vector. So in that case, we can say this is 1 times what we started with. And so we have that for this case, our lambda is 1. All right. Now, one more to check. Okay, so we have minus 6, minus 7, 7, 2, 3, minus 2, minus 4, 5, 0, 1, 1. 0, 1, 1 equals, okay, we're going to get 0 minus 7 plus 7. 0 plus 3 minus 2. 0 minus 4 plus 5. All right, all together, well, negative 7 plus 7 is 0. 3 minus 2, 1. Negative 4 plus 5, 1. Ah, the same as we had before. It's just like the previous one. So in other words, this is 1 times 0, 1, 1. And so we say, okay, great. This also is an eigenvector. Woohoo! Cool. So all of these are eigenvectors. Thumbs up. Now, what does that tell us? Well, it tells us we have 3 candidate solutions. What are they? Well, here you'd have e to the eigenvalue t. Now, e to the 0t is just 1, so our first solution, x1, would be simply a constant times 7 minus 2, 4. Our second solution we have is e to the eigenvalue t, so that's e to the t, times 1, 0, 1. This solution would be what? Well, again, e eigenvalue t, eigenvector. Okay, so we have 3 solutions. Now, that's cool, because we kind of want 3 solutions. It's a 3 by 3 system. However, there's one small detail. Do we have 3 distinct solutions? In other words, linearly independent, or just our more intuitive way of saying things, does each solution actually contribute something new? Because if they didn't, well, it's not going to help us. Okay, so we need to check that. And how do we check whether or not we have our solutions are helping us? We use the Wronskian. So let's check our Wronskian. And so we're going to take the Wronskian here of x1, x2, x3. So remember, that says what? In the first column, first solution, 7 minus 2, 4. The second column is the second solution. Now, it's not just the 1, 0, 1. You have to multiply the e to the t in. So it's e to the t, 0, e to the t. The third column, third solution. So again, don't forget to multiply the e to the t through. 0, e to the t, e to the t. All right, so it's a 3 by 3 matrix. We can do that. That's okay. That's within our capabilities. So remember, for 3 by 3s, we get diagonals in 2 different ways, and we just have to make sure to keep track. So let's do our diagonals going downhill, if you like. 7 times 0 times e to the t is 0. E to the t times e to the t times 4, well, that would be 4 e to the 2t. 0 times negative 2 times e to the t, 0. Ah, I like 0. That's great. So those are going in that direction. Now we're going to go in the other direction. 4 times 0 is 0. We went that direction, so we subtract 0. Oh, look, these zeros cancel. Ah, I'm just kidding. They were already 0. All right, anyway, sorry. Back, serious face. Okay, e to the t, e to the t, 7. So that would be e to the t, that's e to the 2t, so it's 7 e to the 2t, but of course, because we're going in that direction, subtract 7 e to the 2t. And then our last thing is we have e to the t times minus 2 times e to the t. Well, again, we got e to the 2t, and there's a minus 2, so minus 2 e to the 2t. So we're going to subtract minus 2 e to the 2t. Well, the good news is everything that we need to worry about has e to the 2t, so we can ignore the zeros. Minus minus makes a plus. So we have 6 e to the 2t, subtract 7 e to the 2t, which makes a minus e to the 2t. Now, what do you know about e to the 2t? And remember, what do we care about the Wronskian? We care about 0, non-zero. E to the 2t, non-zero. Which means we have a full set of solutions. So, woohoo! Nice! So now that we know we have a full set of solutions, in other words, we have 3 linearly independent solutions, we know how to write the general form. We just simply do a combination of those 3. So, finally, our answer is we have x is some constant, our UC, times our first solution, 7 minus 2, 4, plus some constant d, e to the t, times our second solution, plus some constant e, e to the t, times our third solution. All right. And done. What's the punchline here? The punchline here, why did we do all of this, was we have repeated eigenvalues, but we didn't need to bump. There was no extra factor of t. Why? Why did this happen? And will it always happen? Well, the answer to the second question, will it always happen, is no. There are still problems. And but why did it work here? Well, essentially what happened is we're in 3 space, and it can happen that we have eigenvectors associated with the same eigenvalue that point in different directions. So you had one eigenvector doing this, and then another eigenvector doing something like that, where these are fundamentally different solutions in that they point in different directions. So because you had these extra eigenvectors, enough eigenvectors, life was good. Contrast that to the case when we really have a function with a single variable. You see on the line, what do we have? Well, we just have one direction, right? We only have the line, because if I move in this, I can move any multiple of that, including negative. So for the line, there's no freedom of having multiple directions to go in. And that's why when we encounter for constant coefficients, differential equations, when we had repeated roots, we always had to bump. We had no freedom. Here, we may have to bump, but sometimes we're okay. So let's take a look at another example and see when things do break down. So let's find all eigenvalues and eigenvectors for the matrix 5, 4, minus 1, 1. All right, well, we always start with eigenvalues. You can't find eigenvectors until you found eigenvalues. So we say, okay, we're going to take the determinant of a minus lambda I. Well, that's the determinant 5 minus lambda, 4 minus 1, 1 minus lambda. So again, minus lambda I just says subtract lambda off the diagonals. So 2 by 2 determinants. We've done these before. We're not too worried by these. 5 minus lambda, 1 minus lambda, subtract minus 1 times 4. All right, so that would give us what? Well, 5 minus 5 lambda minus lambda plus lambda squared. Then we have minus 4 makes a plus 4, which is lambda squared minus 6 lambda plus 9, which means we have lambda minus 3 squared. All right, so we have 3 is our only eigenvalue. It's a repeated eigenvalue. Okay, so our eigenvalues are 3 and 3. Okay, now after our eigenvectors, we have 2 eigenvalues. So in order to make things work well, we need to have 2 distinct eigenvectors. Now, we'll get into what I mean by that, but let's carry through here. So we're going to take a minus 3i. So a minus 3i, well, that's what? It's, you can just come up here to reference. Think of lambda is 3, so that would be 2, 4, minus 1, minus 2. And we want to have something, whoops, we want to have, this is our a minus lambda I. We're looking for something where we get 0, 0. All right, so whatever goes here, this would be our eigenvector. Now, we can spot one pretty quickly, or we can find one pretty quickly, right? Because we have our shortcut for 2x2s. Namely, pick a row. I kind of like the second row because it has smaller numbers. Write it in reverse order. Flip a sign. All right, so 2, negative 1, that's an eigenvector. Great. Okay, so we found one. So, okay, now, is there another one? Well, sure, we can do all sorts of things. We can multiply by negative, we could have negative 2, 1, or, we could have used the other row, in which case we would have had 4, negative 2, or many, many other possibilities. But the thing is, these are essentially the same up to scaling. In other words, they're not new eigenvectors. They're the same eigenvectors which have been multiplied by a constant. We really need a second eigenvector which is not the same up to scaling. And is that possible? Well, all right, we can figure that question out. So let's do it by saying, okay, suppose we have 2, 4, minus 1, minus 2 times a, b. Okay? And we want this to be 0, 0. Let's just see if we can figure out anything else. Well, this would tell us 2a plus 4b equals 0. And then this would tell us minus a minus 2b equals 0. Now, what do you notice about these two equations? If I multiply the bottom one by a minus 1, and let's say I divide the top one by a 2, this would say a plus 2b equals 0. That's dividing the top one by a 2. Multiply the bottom by a negative, a plus 2b equals 0. We really don't have two equations. We really have one equation. I would say, oh, okay. So what does that tell us? Well, it tells us here that it says, look, if we look at a, that's always going to be minus 2b. So our eigenvector ab will look like minus 2b, b. And then we can pull out the b. So this looks like b times minus 2, 1. So we are always going to have all eigenvectors look like some scaling factor times minus 2, 1. There aren't two eigenvectors. We're coming up short. That's where we run into issues. So it's not that we have repeated eigenvalues, it's we're missing eigenvectors. All right, so I want to note two things. And so let me grab a pen. Okay, so two comments. So we have some context. Comment number 1. The issue is missing eigenvectors. That's where we have problems. Okay, so when we talk about having to bump, it's not because we have repeated eigenvalues, it's because we have missing eigenvectors. So what does that have to do with repeated eigenvalues? And that's comment number 2. And here's the fun fact. We can only have missing eigenvectors if we have repeated eigenvalues. So that's why we talk about our repeated eigenvalues as like, oh, we have to deal with that because it could be the case that we're missing our eigenvectors. So that's why we phrase our discussion in terms of repeated eigenvalues. Now there's one other comment I want to make. I know I ran out of room. I'm going to say this out loud. For the case of 2 by 2s, in other words, the ones we want you to at least nail it down. If you do have a repeated eigenvalue, things are going to break down. So unless it's the most trivial of trivial, which we would not give you because we love you, we don't want to give you trivial things. So if you do see repeated eigenvalues for 2 by 2s, expect missing eigenvectors. So we still have the question, how do we handle this? What do we do? And you might say, wait, why is this even a problem? Well, it's a problem because we only have one eigenvalue eigenvector pair, which means we only have one solution right now. So if we did x prime equals ax, we couldn't do it because we don't have 2 solutions. We only have one. Where's our second solution? So let's start looking at that problem. So here we go. We have a missing eigenvector. So what does that mean? Well, we're going to be 2 by 2 matrix. We have our matrix, and the only eigenvalues are repeated, lambda, lambda. And we only have one eigenvector, which means we only have one solution. What's the other one? Okay, so now we say, well, let's step back and try to do what we did before. So when we had this problem before, we said, hey, idea, multiply by t. Okay, cool. So first guess. Because, you know, if you're trying something, you should always say, look, let me try what worked before. Surprisingly often, what worked before will either work again or it'll get you closer to something which will work. So we say, okay, t e to lambda tv. Cool. Now, some bad news. Doesn't work. Why? Well, there's 2 issues. The first issue is if you work out the Wronskian, it will always be 0. And there's a couple ways you can think about this, but I'm going to do it with a little bit of hand waving, which is to say, if I look at these 2 functions, which are vector functions, they differ by a scaling factor. Namely, they differ by the scaling factor of t, which means that they're pointing in the same direction. But more importantly, they're not linearly independent, which means the Wronskian will be 0 because they're not fundamentally different. Okay, so that's my hand waving. You can always go and work it out, but there's another reason it won't work, is you plug it into the differential equation, right? Because if you have a guess, what should you do? You should verify. And to verify means plug it in. So you say, okay, plug in x into x prime. Well, the only place t shows up is in the front, so product rule. And the derivative of e to lambda t, a lambda comes down, so you have lambda t, e to lambda tv, and then the derivative first will be 1, so you have e to lambda tv. And then you have, okay, well, what do we know about a times x? Well, the t e to lambda t just pumps out in front, and then you have a times v, which is lambda v. And you say, okay, cool, this matches, and that matches, but what doesn't match? Well, the problem is, you got this piece right here, and that doesn't line up. So it's not satisfying the differential equation. So you say, oh. So let's fix it. And you know, that's how you often try stuff, right? You try something, it doesn't work. All right, can we fix it? Well, maybe. What do we need to fix? Well, we need to get something so we're okay with that. So here's an idea. We say, look, we like the first part. We'll add a correction term. It will also look like e to the lambda t, but now, instead of multiplying by the eigenvector, we'll say there's some vector, w. We won't say what w is yet. We just will say there is something. And let's plug it in, right? Always, when in doubt, plug it in. So we can take x prime, and it's very similar to before for the first part, and then when we take the derivative of e to the lambda t times w, it's lambda e to the lambda t times w. All right, now what about a times x? Well, okay, same as before. You get the lambda t, e to lambda t v, and then you get e to lambda t, a times w. Now you say, all right, what needs to be true? Well, you'll notice these parts already match. So we don't need to worry about those. What doesn't match? Well, what doesn't match is the pieces on the end, namely these parts here. All right, so let's think about this. We need to have the following, namely, we need to have e to the lambda t times our vector v plus lambda e to the lambda t times our vector w needs to be equal to e to the lambda t a times w. Now, what do they have in common? E to the lambda t. So what can we do? We can get rid of it because it's a common thing. So away it goes. So now we say, oh, hey, check it out. What do you have at this stage? We have v plus lambda w is a times w. And the cool thing is there's no t in sight. Well, why is that nice? Well, it means this is no longer a problem about calculus or functions. It's purely just an algebra problem, a matrix problem. Nice. Okay, so we're almost to where we have our rearrangement. So what do we want? We want a times w minus lambda times w is equal to our vector v. And now we say, okay, well, how would that work? Well, we want to pull out w. We do our same trick that we did previously, which is to say, well, to help us pull out our w, we're going to add a factor of 1. Well, actually, it's a factor I. So we have an I, and that lets us pull out our w term. So a minus lambda I times w equals v. All right. So, great. So if we can find such a w, then we say this second guess will work. Is there such a w? Great question, and we'll see about that. All right, maybe it's time for an example. So let's go back to something we were working on. This matrix here, 5, 4, minus 1, 1, might look familiar. Yeah, it should be. In fact, it's the same matrix we were working on previously. So we actually know a lot about it. And so our goal is to say, find the general form for solutions of x prime equals 5, 4, minus 1, 1, x. Now, because we've worked on this, let's not repeat our work, and let's just put in what we already know. So from previous work, what do we already know? Well, we have a couple of things. We know that our eigenvalues are 3 and 3. Okay, great. And we know that there's one eigenvector and only one eigenvector, and that was the vector 2, minus 1. All right, so that's what we know. Okay, so now from what we just talked about, we can call these various things. Here we have our lambda, here we have our v. So we have our two solutions will look like the following. We know one of them already. It's going to be e to the lambda t v, and the other one will be t e to the lambda t v plus e to the lambda t w. Now, we know a lot of pieces. We know lambda, we know v, we need to know w. So the only thing that we're missing here is to say, okay, what do we need for w? Well, if we copy what we had from what we just talked about, what we need is w satisfies the following, namely, we look at a minus lambda I times w, and we should get out our vector v. Okay, so that's our goal. Now let's look at our matrix here. So I'm going to take a minus lambda I. So I'm coming here, and what will that be? Well, that will be our, we're subtracting 3 off the diagonal. So 2, 4, minus 1, minus 2. And I want to multiply by something, and I want to get out 2 minus 1. All right, so do you see a vector that works? Now, there should be a couple of vectors that work, but the punchline for this is that this vector that you see here will look suspiciously like our columns. In other words, it's like a multiple of our columns. So you just have to say, look, you know, how do you scale our columns in some nice way and get that? And there's not a correct answer for w. We'll talk about that in a second, but we just need one for now. All right, so what can we pick? Well, I claim it's 1, 0. So when we write 1, 0, it says I want one of these and I want 0 of these. So multiplying a matrix by a vector says I want this much of the first column, that much of the second column. And if you carry out the multiplication, you'll see, yeah, you get 2 plus 0, which is 2, minus 1 plus 0, which is minus 1. All right, so we say, aha, we found w. And now we have our solutions because we have our pieces. And so because we've done all the work, we talked about the theory, now we're ready to write our answer. So we have the following. We'll take our two solutions. Let's go ahead and rewrite them here. So this would be e to the 3t times 2 minus 1. And this one would be e to the 3t, 2 minus 1, plus e to the 3t times 1, 0. All right, good. So our general form will be what? Our x will be some constant, e to the 3t, 2 minus 1, so first solution, plus some other constant times our second solution. Well, that's a little bit longer to write out, but we just have to copy. And all right, good, done. Now, you might be suspicious of a couple of things. Perfectly fine, very reasonable. One thing you might say, is this really a second solution? You're not like trying to trick me, are you, Steve? And first off, yes, it definitely is a solution because it matches the theory. The theory says that this will work. Is it a second solution, or is it something that we've already have? That's actually a fair question. How could you check? The Wronskian. So, you know, we have time. We have all the time we want. We're among friends. And so if we did a quick check with the Wronskian, what would we have? So if you called this first one, let's say x1, and the second one, let's say it was x2, then our Wronskian of x1, x2 would be, well, we'd have 2e to the 3t minus e to the 3t. And then here we'd have 2t e to the 3t plus e to the 3t, and then minus t e to the 3t. All right? So that becomes, okay, we'll have minus 2t, e to the 3t times e to the 3t becomes e to the 6t. You add the exponents. Then we're going to subtract. Now here, we'll multiply by minus e to the 3t, so it'll become a minus 2t e to the 6t, and then minus e to the 6t. Well, what do you notice? The first two terms cancel. Minus minus makes plus. And this is not 0. So yeah, so it truly is a second solution. It's fundamentally different from the first solution. And it does satisfy what we need to be a solution. And so yes, this is it. This is the general form. All right, good. So okay, wait, maybe we should recap. So our strategy when we have repeated eigenvalues will be as follows. And we're going to focus on the 2 by 2 case. So if we have eigenvalues lambda lambda, step 1, we find our eigenvector. We should anticipate there will only be one. Okay, so that solves a minus lambda I times v equals 0. Great. Step 2, we need to find another vector w, so that a minus lambda I times w is equal to v. All right, and now, after you've done that, our solutions are, well, the one that we're used to, e eigenvalue t eigenvector, and our second solution is where we've bumped up our first solution, added a t, and then added a little fixing term, and then e to lambda t times w. All right, now some comments. Our choice for w is not unique. In other words, there's lots of choices that we could have made. And you might say, well, what does that mean? Well, the statement means, look, any two choices of w will differ by a multiple of v. Now, why is that? Okay, so let's just figure this out. So here's the claim. We say, look, if we have a minus lambda I, and I'll say w1 equals v, and we have a minus lambda I w2 equals v. Okay, so suppose we have two w's. So here are two w's. Now we're going to subtract. So when we subtract, what happens? Well, because we have the a minus lambda I in common, we become a minus lambda I, and then it's really w1 minus w2. That's the left hand. On the right hand, v minus v is 0. So we have, oh, a minus lambda I times something is 0. Well, what kind of thing, when you multiply by a minus lambda I, gives you 0? And it turns out that there's one thing that does it. And that's anything that's a multiple of the eigenvector. Because remember, how do you find the eigenvector? It's a minus lambda I times something equals 0. So this is some multiple of v, which is to say that, oh, if you look at w1 minus w2, it's just some multiple of v. Or you could say, well, look, w1 is w2 plus a multiple of v. So that's what this statement means. And so you say, okay, if you added a multiple of v, well, what could you do? Well, the punchline is you could distribute your constant in. So here b is a constant. And then you say, oh, all right. Then you can move it to the first term. And then you have, what you had before. Now, this is a lot of hand waving to say the following more simple thing, which is to say, since you have choices for w, pick a simple w. Find the easiest thing which works. Don't try to be complicated. Complication is not a good thing when you're trying to work a problem. It's a fun thing in class to say, ha ha ha, let's choose 1,000,000 and 1,000,002. Yeah, okay, fine, we can joke about it. But on a test, you're like, no, be simple. The simpler something is, the less likely errors will come up. So you have choices for w, pick the simple choice. Now, we have been focused on the 2 by 2 case. Can bad things happen in 3 by 3? Absolutely they can. You can be missing eigenvectors for 3 by 3. And in fact, things can get a lot more interesting. And the higher up you go, the more interesting it gets. And the problem here is that when we say it's more interesting, you have to get into a little bit more of the theory of matrices. And it gets a lot more subtle. So we're going to avoid that discussion for now. And if you ever want to follow up on that discussion, first get familiar with linear algebra, and then you'll be able to carry out and see what happens. All right, I think we have time for one more example. Solve for x of t and y of t, satisfying the following system. X prime is 5x plus 9y. Y prime is minus x minus y. And we're told x of 0 equals 0 and y of 0 equals 2. So since we've been talking about using our matrix methods, first thing, let's turn this into a matrix problem. So we're thinking about this as x, y prime. We'll grab our coefficients, 5, 9, minus 1, times x, y. We're like, okay, cool. The x, y, we'll give that a name. And oftentimes we just use x again, but that can be confusing. So let's go ahead and give it a different name. We have lots of letters of the alphabet. We can go ahead and call it z prime. Yes, it is not just prime, it is z prime. All right, so 5, 9, minus 1, z. Okay. All right, good. Okay, well, we're ready to begin. Oh, by the way, our initial conditions here, we should point out, is that what happens? Well, z of 0, that's really x0, y0, because z is xy. So if we plug in 0, that's x with 0 plugged in, y with 0 plugged in, and that's equal to 0, 2. Okay. All right, we're ready to begin. Okay, so first step, eigenvalues. Anytime you have a matrix problem, your first reaction will be, I got to know the eigenvalues. And depending upon what the eigenvalues are, there's actually going to be different roads you take. We kind of know it's repeated, but let's pretend we didn't. So we again take our determinant, a minus lambda I, that's the determinant, 5 minus lambda, 9 minus 1, minus 1 minus lambda. All right, that's 5 minus lambda, minus 1 minus lambda, subtract, negative 1, oops, times 9. I don't know why I put a minus there. All right, so minus 5 lambda, plus lambda squared, plus 9, which gives us lambda squared minus 4 lambda and plus 4, which is lambda minus 2 squared. Set that equal to 0, and we say, aha, our eigenvalues are 2s. 2 and 2. So our eigenvalue repeated. What are the odds? All right, very high. But, all right, what comes next? Well, once we know we have repeated eigenvalues, we've got to put ourselves into our oh, we've got repeated eigenvalues mindset. So the next thing for us to do is to say, all right, let's look for eigenvector. And we know, because this is not trivial, and it's 2 by 2, repeated eigenvalues means there's only going to be one. So we look at our a minus lambda I. So, again, I like to use this as a reference. That would be 3, 9, minus 1, minus 3, times something needs to give 0, 0. All right. Well, what's going to work? What's going to work? Well, pick the second row. That has nicer numbers. Write it backwards. Flip a sign. 3, negative 1. All right, so we now know that we say, great, our eigenvector v is 3, negative 1. Now, we need to find our second solution. Because we have our eigenvector, we only get one solution. Our eigenvector eigenvalue, our second solution is going to come from doing what we've been talking about, where we say, okay, well, at this stage, we're going to take our a minus lambda I, which we already have. So we say, okay, we need to find 3, 9, minus 1, minus 3, times something to get the 3 minus 1. So that goes there, and whatever we find, that's what we call W. Okay, so this will be our W. Now, here's the thing to remember. When you're trying to figure out W, you just need to find something that works. And oftentimes you say, okay, pick a column, and you say, if you want that column, or multiple that column. Well, 3 minus 1, that matches up with 3 minus 1. It says, look, I want a copy of this column, and I don't want anything from that column. So 1 copy of the first column, and nothing from the second column. Okay? All right, so there we go. There's our W. All right. Whew. Now we have our pieces, and we have to remember how our pieces fit together. Well, what happens? We get the following. Our first solution, x1, will be our e to the lambda t v, which in our case, lambda is 2, and our v is 3 minus 1. So e to the 2t, 3 minus 1. Our second solution is going to be t e to the lambda t times v plus e to the lambda t times w. All right. So, well, we take our first solution and we've bumped it up by a factor of t, but then we say, wait, in order for it to work, we also need to have a little bit of correction. Now, in both our examples so far, we've been able to use 1, 0. You may not. I don't want you to say, I've cracked the code. This will always be 1, 0. There's actually a way to always make it 1, 0, but that's a different story. Just be careful. Make sure it satisfies the relationship that you need it to. All right, so we're ready to write down the solution in general. Okay, so here we go. Here we go. Our general form will look like the following. Namely, we're going to have x is some constant c, e to the 2t times 3 negative 1, plus some constant d, t e to the 2t times 3 negative 1, plus e to the 2t, 1, 0. Okay, good. Are we done? No. Why not? Initial conditions. Okay, so the next thing for us to do then is tackle those initial conditions. All right, well, we can plug in 0. And whoops, I was putting in x's, We should have been calling them z's, and I apologize for that. That's my bad. I got distracted. Okay, so what do we have? Well, when we plug in 0, we will get z of 0 equals, e to 0 is 1, so we're going to get some constant c times 3 negative 1. And now, plug in 0, we get 0, so that term goes away. E to 0 still 1, so we end up with some constant d times 1, 0. And that has to equal, z of 0 is 0, 2. Okay, so that tells us, well, we have 3c plus d equals 0, and minus c plus 0 equals 2. And now we're like, can we solve this system? I think we can. Look, we see here that c is negative 2, right? Just multiply both sides by negative. All right, if c is negative 2, we get minus 6 plus d equals 0. So we say, oh, d is 6. All right, well, so now we get our answer. Namely, z is equal to minus 2 e to the 2t times 3 minus 1, and then plus 6, and I'm going to have to move this over to squeeze it in. All right, 6, we have our t e to the 2t, 3 negative 1, plus e to the 2t, 1, 0. All right. Whew. But we're not done. Okay, wait, what? Well, we have the z. The problem didn't start with the z. We introduced it. So we're not done until we get back to x's and y's. So how do we get there? Well, we're going to just put all of z into one single vector. All right, so let's see, what would that vector look like? Well, we'd have a minus 2e to the 2t times 3. That's minus 6 e to the 2t. Then here, multiply the 6 times t e to the 2t times 3. That'd be a plus 18 t e to the 2t. And the 6 times e to the 2t times 1 would be a 6 e to the 2t. Then downstairs, we'll get a minus 2 e to the 2t times minus 1, 2 e to the 2t. 6 times t e to the 2t times minus 1, minus 6t e to the 2t. And then e to the 2t times 0 is times 6, don't forget. Well, you'll still get 0. Upstairs, the e to the 2t's times the 6's, those cancel. So we're left with our 18t e to the 2t upstairs, and our 2e to the 2t subtract 6t e to the 2t downstairs. And, well, we have a little tiny space here in the corner. So our final answer. All right, how do we do it? Well, remember, this is z, which looks like x, y. So we have that x is 18t e to the 2t, our first top entry. And that y is our 2 e to the 2t subtract 6t e to the 2t. Done. Done. We made it. We fit it on a page. Whew. All right. Well, I know this is a little bit to digest, but I want you to sort of finish on a positive note. Positive note number 1, you can do this. It takes a little bit of practice. You have to remember a few basic things, but you do it a few times, you'll remember it. Positive note number 2, come back next time and we'll have something which is far better, super fast, and you'll be like, why didn't you tell us this from the start? And we'll just be like, sorry, we just needed to learn. So there's actually another way to do things with repeated roots that works surprisingly well and is really cool and super beautiful. And that'll give you reason to come back next time. So I guess I'll see you then.